The Earth's surface seems solid, dependable. We build our lives on it. But beneath our feet, a different story unfolds. The Earth's crust is a jigsaw puzzle of massive tectonic plates constantly shifting and grinding against each other. This movement, often slow and imperceptible, builds up immense pressure along fault lines. When this pressure exceeds the strength of the rocks, the Earth's crust ruptures, releasing energy in waves that shake the ground, an earthquake. Imagine snapping a twig. The bending builds up energy until suddenly the twig snaps, releasing that stored energy. Earthquakes are similar, but on a much grander scale. The energy released travels through the Earth's crust and upper mantle as seismic waves. These waves cause the ground to shake, sometimes violently, and can travel thousands of miles from their origin. The point within the Earth where the rupture first occurs is called the hypercenter or focus. The point directly above it on the Earth's surface is the epicenter, where the shaking is usually felt most intensely. Earthquakes remind us that our planet is dynamic, powerful, and sometimes unpredictable. Understanding these events is crucial for mitigating their risks and building safer communities. Earthquakes are classified by their magnitude, a measure of the energy released during the rupture. The Richter scale, developed in the 1930s, was an early attempt to quantify earthquake size. Today we use the moment magnitude scale, or MMS, which is more accurate for larger earthquakes. The MMS is logarithmic, meaning each whole number increase represents a tenfold increase in wave amplitude and about 32 times more energy released. A magnitude 3 earthquake might feel like a truck rumbling by, while a magnitude 7 can cause widespread devastation. History is filled with examples of devastating earthquakes. The 1906 San Francisco earthquake, with an estimated magnitude of 7.9, leveled much of the city and ignited a firestorm that burned for days. The 2011 Tōhoku Earthquake off the coast of Japan, with a magnitude of 9.0, triggered a massive tsunami that caused widespread damage and claimed thousands of lives. This event also highlighted the interconnectedness of natural disasters and the potential for cascading effects. Scientists study past earthquakes to understand their patterns and potential impacts. This knowledge is crucial for improving building codes, developing early warning systems, and educating the public about earthquake preparedness. Earthquakes can trigger other devastating events such as tsunamis and aftershocks. Tsunamis are giant waves, often mistakenly called tidal waves, caused by the displacement of large volumes of water. An undersea earthquake can cause the seabed to rise or fall, displacing the water column above it, and generating a series of waves that travel outward in all directions. These waves can travel across entire oceans at speeds of up to 500 miles per hour, resembling jetliners in their velocity. When they approach shallower coastal waters, they slow down but increase dramatically in height, often reaching tens of feet. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake, highlighted the destructive power of these waves. Aftershocks are smaller earthquakes that occur after a larger main shock. They are caused by the Earth's crust adjusting to the stresses caused by the initial rupture. Aftershocks can continue for days, weeks, or even years after a major earthquake, posing a significant hazard to rescue and recovery efforts. They are a constant reminder that the danger doesn't end when the shaking stops. Earthquakes are not randomly distributed across the globe. They occur most frequently along tectonic plate boundaries where the Earth's crust is under the most stress. The Pacific Ocean's Ring of Fire, a 25,000-mile horseshoe-shaped zone, is home to about 90% of the world's earthquakes. This zone is where the Pacific Plate interacts with several surrounding plates, resulting in frequent seismic and volcanic activity. Other notable earthquake zones include the Alpine Belt, which stretches from the Mediterranean region eastward through Asia, and the Mid-Atlantic Ridge, a divergent plate boundary running down the center of the Atlantic Ocean. Living in an earthquake-prone area requires a unique awareness of the risks and a commitment to preparedness. Building codes in these areas often include stricter seismic standards, and residents are encouraged to have emergency plans and kits.